Welcome to Spring LIB.
Hi guys, so problem 38.31 asks us to find the momentum of an electron after a photon is scattered off of it. So we can see how I've set up this problem in this little sketch in the top left. So we have a photon, which is this squiggly red line coming in, hitting the electron, which is this black circle, and then scattering off, which is this second squiggly red line at an angle of 60 degrees from how it initially came in. So we can start with this equation, lambda prime minus lambda equals h over mc times 1 minus cosine phi. So here, lambda prime is the wavelength of the scattered photon, lambda is the initial wavelength of the photon, h is the Planck constant, m is the mass of the electron, and c is the speed of light, and then phi is that angle between the initial photon and the scattered photon. So we can rewrite this to get the new wavelength in terms of all the other variables. So lambda prime equals lambda plus h over mc 1 minus cosine phi. The initial wavelength is given to us in the problem statement. It's this 0.1050 nanometers, or 1.050 times 10 to the negative 10th meters. I've written out what h, m, and c are over in this box on the right, and then again phi is 60 degrees, so cosine of phi is cosine of 60 degrees, or 1/2. So we can plug in all of these numbers and we get lambda prime is 1.050 times 10 to the negative 10 meters plus h over mc with those values is 2.43 times 10 times 10 to the negative 12 meters, and then times 1/2 from that cosine. And the final answer is lambda prime equals 1.062 times 10 to the negative 10 meters. So now that we have this new value of lambda prime, let's look at the momentum of the system. So we can start by, let me just redraw this sketch so we remember. We have the electron, photon comes in, photon scatters, and this angle is 60 degrees. Okay, so let's start looking at the initial momentum of the system. So in the x direction, our initial momentum, hitting the edge of the whiteboard there, Pix. So in our initial system, the electron is at rest. So that means that all of the momentum is coming from that photon. We have the problem set up such that it is moving along the x direction, so all of its momentum is in the x direction, and we know the momentum of a photon, I'll just write it up here, is P equals h over lambda. So all the initial momentum is from the photon, it's all in the x direction, so our initial x momentum is just h over lambda. Now, what about after the collision? So now we have the new momentum of the photon, h over lambda prime now, and we want only the x component of it, so we'll multiply it by cosine of phi. And then we also want to consider the momentum that the electron has now, and we don't know what that is, so we'll just put in a variable for that now called PE for electron x. Okay, now let's look at the y component of momentum. So initially, again, all of the momentum in the system is coming from just the photon, and we have it set up so that the photon is moving along the x direction, so there's actually no y momentum initially. So we just set Piy equal to 0. And now for P final y, we again want the component of the photon momentum, but this time along the y direction, so we multiply by sine phi instead of cosine phi. and then we include the y momentum of that electron. So due to conservation of momentum, we know that the initial momentum in the x direction should be the same as the final momentum of the x direction, and similarly for y. So we can set these things equal to each other. So we have p I x is h over lambda equals p f x, which is h over lambda prime cosine of phi plus p e y. So we can rearrange this equation to solve for the, PEX. So we can rearrange this equation to solve for the x momentum of the electron after scattering. So we get PEX is h over lambda minus h over lambda prime times cosine phi. We can plug in our numbers from the last part, so we have h over 1.05 times 10 to the negative 10 meters plus, again, cosine of 60 is 1/2, minus 1/2 h over that new lambda, which was 1.062 times 10 to the negative 10 meters. And solving this using that value of h from the last screen, we get PEX is 3.191 times 10 to the negative 24 kilogram meters per second. Okay, so now we can do the same thing for the y direction. So we have PIY, which was 0, equals P final y, which was h over lambda prime times sine of phi plus PEY. So we get now PEY equals negative h over lambda prime sine phi equals sine of 60 degrees, which is square root of 3 2. Yes, square root of 3 over 2 times h over lambda prime, which again is at 1.062 times 10 to the negative 10. And we find, negative here. And we find finally PEY is negative 5.403 times 10 to the negative 24 kilogram meters per second. Okay, so now we have the momentum of the electron after scattering. We have its x and y components, so we're nearly there. But the problem actually asks us for the magnitude and direction of the momentum. So we need to combine these to get the final answer. And I'll just rewrite. So we have it, the x component, which was 3.1 3.191 times 10 to the negative 24 kilogram meters per second. All right, so to get the magnitude of the electron momentum, we just do PE is the square root of PEX squared plus PEY squared. And plugging in these values for PEX and PEY, we get 0.28 times 10 to the negative 24 kilogram meters per second. And now for the angle, we know that tangent of the momentum angle is PEX over PEY. So theta, this angle, is the inverse tangent of that fraction. And plugging in the numbers, we find that theta is negative 59.4 degrees. So that's our final answer, and we can go back to that initial diagram. So we have the photon coming in and then scattering, and we know this angle was 60 degrees. So the angle of the electron momentum is 59.4, so it's almost back to back with that scattered photon, but slightly lower, so it would be going roughly in that direction. So there we go, there's our final answer. Thanks.